welcome all of you guys. I hope you hear me. I'm trying to speak a little bit louder. I am Alex. I'm from Berlin, Germany. And I'm one of the grantees who got some funding to create a new block explorer for Tezos. That explorer is called TzStats. Some of you might have seen it already. And what I'm talking about today is the back-end side of it, because that's actually a little bit more fascinating than the front end itself. But I come back to the front end when you have questions. So let's just jump into. The block explorers you know today are mainly used for one purpose: to look what's going on a blockchain. Yeah? Most of the time you have them for public networks. But it makes also sense to have the same kind of block explorers people are used to for private networks, where people develop their own private smart contracts, test them out before they publish them live. They also have the need to have some sort of visibility into the blockchain. Then there is a lot of dApps that when they are live and when they grow big, they really need to put their operational systems on some sort of an infrastructure that kind of can grow with them, that scales with their use case. And after the fact, we will have many people who need to be compliant in their industries, and auditors who need to make sure that people kind of acted in a compliant way. And for these kind of users, we also need special tools so that they can have a look at large quantities of on-chain data in a very efficient and very easy way. And lastly, all the researchers and analytics companies, law enforcement, whoever has kind of a stake in these systems needs some sort of access. So today, Block Explorer backends are built in a certain way to optimize the amount of time it takes to implement things. People would use a regular database, like most of the time a SQL database, because they know how to use it. People would also try to minimize the time it takes for them to extract the data out of the blockchain and put it into the database. And since they don't really know their use cases in the beginning, they think, okay, let's just take out all data from the blockchain and think about the queries and the extraction after the fact, later on. So we end up usually with a structure where we have the center of everything is the SQL database, and you have some sort of job which is called ETL, extract, transform, and load. So it extracts data from the blockchain, transforms it a little bit, and loads it into a database. That's what's happening. And for expensive queries, usually once a day, like you see this on TzScan, they do offline queries. Maybe against the SQL database, or sometimes also maybe against the blockchain nodes. And then you have the API on top, which kind of provides all the data to front ends. What's wrong with this approach? So right now, blockchains are small, they are tiny. You can use any approach in engineering and you still get a working solution that is also relatively fast. But when we think ahead, 5 years or 10 years, the current system just crumbles to a halt because the amount of data is just too massive and too big. And there's a couple of problems here. One problem is that these blockchains, they are not made for really fast access to arbitrary data. So you have slow and expensive queries to state. You have, in these current shops, because they're so simple, only a one-way flow of data into the database. The databases, they are not the best, or the databases people use, they are not the best abstraction, the best way to describe and store these large amounts of data. Because SQL databases store everything in a row, like all the fields in a table that belong to a row are stored together. But when you only want to look at 2 columns and you want to aggregate kind of 1 million rows across 2 columns only, a SQL database would still load all data from disk, which is a massive waste of time and resources. And because of that, you also have limited throughput to your downstream application layers. So that's kind of a lot of pain points. but simple to make. Entering the next generation of Explorers or Explorer backends I created. The next generation works in a totally different way. It also extracts data from a blockchain, but instead of looking at all the different context information and the addresses, it only looks at the receipts, the block receipts, and reconstructs all content and all state from what it observes. I call it a fat indexer. It's kind of a bigger structure, but in addition to ETL, it analyzes the data, it verifies that the data is correct, and it can provide live reorganization, blockchain reorganization updates. So when a blockchain reorganizes, this indexer can follow along live. So you always have live state in a couple of milliseconds, close to what the blockchain sees. Under the hood, there is a very efficient and new type of data store I have implemented over the last 1.5 years, and this is the first commercial project that actually uses this data store. We will see some performance numbers later on, and most of these performance numbers are only possible because this data store is so efficient. And one of the things that this data store allows to do is not only provide an Explorer-like API where you have single objects that you can query, but what I could also do is I put a table API on top and a time series API that allows you to go through millions of rows in seconds or milliseconds. And this is kind of an impressive thing because that allows me to think about which data I store in a totally different way. I can store much more data fields, I can do live analytics at every block, and I can store the analytical data as well. This is great. And because this infrastructure is so fast, the blockchain nodes are too slow. So what I had to do is, I had to even implement a caching proxy in the middle to really kind of feed enough data in here. So when there is a change in code and we want to crawl new fields, I usually reconstruct the data of the blockchain in a completely new way. I delete the old database and I run it again. And it only takes 40 minutes for mainnet right now. That's compared to several hours or sometimes even days for other solutions. Why is that so important, or why is that so efficient? Under the hood, this data store uses a columnar design. So every field is stored as a column vector. Like all, say for example, integers or hashes are stored next to each other in a column, and that allows you to make use of CPU and memory buses in a way more efficient way than a regular database. It also uses smart compression, meaning when you have a long list of integers that are close by to each other, they are very efficiently to compress. That's why we achieve a very, very great compression amount, and you will see some numbers later on. And the third is, when you have vectors of data, you can have vector operations in modern CPUs. Every CPU comes with a lot of vector operations, but few applications actually use it. I had to dive a little bit into assembly and did a couple of weeks of assembly programming, and that gave another kind of 20x performance improvement to an already fast data store. And this is amazing. So let's have a look at the numbers. There is one thing that's worse as compared to other solutions, and that's the code size. Because the indexing does a lot more things than a simple extraction and loading into a table. It's much, much bigger. For comparison, the lib indexer from Nomadic, which is a very simple ETL job, only has 1,400 lines of code in OCaml. That's great. It's a very tiny piece of software that does a basic job. Super, it's great. But it uses a SQL database. Conceal also uses a SQL database, but does a more sophisticated job. It's kind of 13x the size of lib indexer. And the Blockwatch indexer does even more during processing, and that's again a 5x more code to conceal, but as you will see on the next slides, it's worth it. And the implementation happens once. But I want you to be able to run your own indexers in your own infrastructure and not rely on third-party services that are somewhere hosted in some cloud environment. Let's look at the storage costs. I don't have comparison numbers for Conceal or libindexer because I didn't run them. But what I have is numbers looking at my own implementations. A Tezos node yesterday night, a full archive node, uses 234 gigabytes of storage. That's a little bit inefficient because they don't do pruning, they don't do garbage collection, but that's fine. The proxy I was talking about extracts RPC data as JSON and compresses it and stores it very flat in a key value store. All this data is 6 gigabytes in size. And the real index with all the analytics that are going on only takes 2 gigabytes in size. That's thanks to the highly efficient data compression in the columnar data store. Let's look at indexing speed. I found some numbers on libindexer. They say, okay, we can do 1,000 blocks per minute, kind of extract and load it into the database. I just did a comparison last night and rebuilt our database for mainnet, and it only took 48 minutes for the entire mainnet, which kind of translates into something like 13,000 blocks per minute. Of course, you don't do this all the time, but the thing here is you can do it on a laptop. You don't need a large server for this. And having the proxy, you don't even have to have an archive node, so you could have the proxy sitting on your laptop, synchronizing live with an archive node on the net or somewhere else, and then run the indexer against this one. So that's a fascinating number, and that's kind of a regular server CPU, just a normal Xeon, and it would only use like 4 CPUs. I didn't get more, I didn't give it more CPU. So query speed, at the other side, how fast you can get the data out of that database. So I have just some examples here. Listing all the balances of all funded accounts. Look, right now in Tezos, like yesterday night, we had close to 300,000 accounts that were funded on the Tezos blockchain. When you would get these balances out of the blockchain node, I did it recently for a QA script. It ran for 3 hours. And when you use this database, this I also checked it, it only takes 1.8 seconds to get the list of 300,000 balances of contracts. So this is kind of an amazing number, but the numbers get even more amazing when you look at, because this table is not big. This is just a 300,000 table in size. The other tables are much, much larger, like all the operations, like 40 million operations that are on the blockchain right now. So I just did another test. I wanted to see how long it takes to find all the activations, like where people activated their fundraiser commitments using their private key. And I just wanted to list them. This is right now, it's 20,761. And this takes only half a second. That's also fascinating. And the same goes for, say, for example, we have a table that stores all the balance updates. Like when you send some Tezos to somebody else, you have 2 balance updates. One you pay fee, and the other you pay, you send the transfer away. And then the other side has 2 updates, or 1 update, fees received. And then maybe delegators have updates for you sending coins to somebody else and paying fee. So all these flows, as we call them, we store in another table, which is the biggest table, kind of several 100 million entries. And when you, say for example, have a query, you look for all the balance updates that are larger than 10,000 Tezos over the entire lifetime of mainnet. That takes 680 milliseconds right now. Yeah? And that already includes the data transfer time. And the same when you do, say for example, a time series query, where you let the database backend aggregate data in a certain time frame. And this is an example for aggregating across all the 600,000 blocks and looking at the volume that has been transferred in each block, but aggregating these volumes per day. So it's roughly 450 days worth of time, but it's 630,000 blocks that have to be kind of loaded from a database and aggregated on a daily basis. And that query takes 1.1 seconds. So with this type of technology, you could kind of imagine completely new ways of analyzing blockchain data. What we did based off this technology is we created an API that would serve a block explorer right now, because that was kind of the first project we were having. But downstream we are thinking of much more use cases. So the entire indexer provides 3 types of API flavors. One is where you can get out single objects and relations between objects, like for example a single account and all the transactions that this account made, or all the smart contracts an account has created. That's the Explorer endpoint. Then we have a table endpoint where you get raw access to these huge tables. And the nice thing about this is you can slice and dice each table as you want. You have a filter for every field in a table, so you can put filters for every column, and you could select the number of columns you want to receive. That way you can control how much data you actually extract from the database and control the time it takes for you to download or fetch the data, and also process it on your end. The nice thing about this database is that it streams the data to you, meaning you send the query, and as soon as the first result is loaded from the data tables, it's kind of sent to you. And as long as more results are kind of found in the database, they are all streamed over HTTP. So you get the first result extremely fast. In, say, for example, you have an end-to-end time 40 milliseconds, you get the first result in 42 milliseconds. And then the rest of the results would flow in depending on how fast your network is and how fast the database is. And the same goes for the time series endpoints, and they in addition allow you to aggregate data by different time frames, like an hour, a day, a month, whatever you like. There is a documentation about this API. I just finished the first part that documents the Explorer side tonight, and kind of the top level information about the 2 others. And there will be more documentation coming soon. What we built with it is this block explorer that uses different parts of this API under the hood to display all the data. That's a separate project here. You could build your own block explorer. You could build your own tools sitting on top of that API. And because it's so efficient, right now we're actually running everything on one server. We have 3 indexers for the 3 networks that we are just crawling right now. And this server is just a 64 gig memory machine with some SSD space, but in the end, it's maybe used to 10–20% of CPU, and maybe only 20% of the main memory is used. So, if you want to get in touch, follow me or send me a DM on Twitter. Our project is called TzStats. It has a Discord, which this is the invite link to. If you have feedback, I'm very happy to answer things. I'm very happy to get feedback. And if you have a project with a massive amount of data, come talk to me. Maybe I can help with this solution. Thanks for your attention, and time for questions. Oh, so yeah, so there is some insights, and let me. So this is a Grafana dashboard that looks into the raw data of the database. That's different from the Block Explorer. The Block Explorer is a low affordance tool for people, not developers, but for normal users to interact with the blockchain. This one is more a research tool that allows us to understand what's going on the blockchain. And there's a lot of interesting statistics you can get out of every blockchain. In this specific case, it's Tezos. I do it for Bitcoin and others as well. But let's stick to Tezos. This one is an interesting metric because it shows how much of the supply has actually moved over the course of the last 3 months, as opposed to the supply that sat still in accounts and wasn't moved. And we see that the amount of supply that moves is decreasing. So there's more and more people holding on to Tezos, and right now it's below 20% of all the Tezos that are kind of fluctuating in the network. That's interesting. Another interesting metric is when you, for example, look at the whale domination. So how many people hold how much, or how many accounts hold how much of the supply. And what we see is that in Tezos, the top 1,000 accounts, they hold 79% of all existing Tezos. That's a lot, but the interesting thing is you have to see this over time. And over time, this number is rapidly decreasing. Like from a year ago, it was above 80, 90%. And this is not the case for every blockchain. Bitcoin, for example, has the same number at 34% right now, like the top 1,000 people. But Bitcoin is still a little bit decreasing, but not so Bitcoin Cash, for example, or Bitcoin SV. They are actually more centralized, or they become more centralized over time. Tezos is becoming less centralized. And those are the types of things you see when you do this on-chain analytics. But just 2 of them. This screen is kind of down to the next floor. But yeah.
Another question, is it static data we should just once upload it, or is some days live as new blocks get baked?
Yeah, so as blocks get baked, as the node bakes new, or as blocks get baked and distributed through the network, our archive node picks them up. And the proxy or the indexer, they would watch for new blocks. So there's an efficient watching mechanism. And as soon as the block is confirmed on the node, the indexer gets the signal and pulls the block out of the indexer and indexes all information that is contained in the block. Updates internal state, updates balances, and makes the data right away available on the API. If there is a reorganization, like one block becomes orphan or 2, then the indexer would follow the reorganization, would roll back the updates and would roll forward the main chain blocks. So everything is live.
Do you use any open source columnar database implementation to make the whole?
I looked at many different columnar database designs for inspiration, but in the end I implemented my own because in the blockchain space, especially because of reorganizations, you have to be able to update different parts, and most columnar data stores won't allow you to efficiently update. And that's one of the reasons why I had to implement an own data store. And the other point is that most of the data stores also don't support all data types. And especially not like this Block Explorer API works in a way you give it a hash of an address and it finds the address in the database. That's because the columnar store has a hash index too. And this is also something you don't find on all columnar data stores. So it's kind of a mix of good designs made even better. More questions? Then thanks, you were a great audience.